Okay.
We have two presentations today as part of our program, Mathematical Theories. The presentation, the short presentation, means for 30 minutes each, by Pavel Chernyshov and Anna Chernyshov. Second, they are PhD students in Tel Aviv University, School of Mechanical Engineering. Okay. They are second year students. They just started third year of their studies. And please.
Okay, hello to all. My topic for today is inversion of waves and current profiles using X-band radar in coastal areas. So let's go further. Basically, what is a marine radar? Marine radar looks like something like this. It is antenna with a conjugation unit which goes to a monitor. And for navigational needs, that's it. You don't need anything else. In order to access data after, you need digitizing block, like A to D converter to write the data to hard drive and then to have an opportunity to make a post-processing. And I want to stress that it's exactly the same radar you use for navigational needs and installed in the top of the ships, like here. This is the photo of Final 3 platform. It's a research platform. They have a lot of radars, and it's rather good place to install the radar because it's pretty high, and it's actually in the North Sea. Let's understand what actually means X-band. X-band, it's a frequency of roughly 10 gigahertz, which corresponds to the wavelength of 3 centimeters. Polarization for transmit and receive could be HH, VV, or cross polarization like HV or VH. Antenna length also varies. Big antenna gives a better azimuthal resolution. Okay, this I discuss a little bit later in details, just to understand the range of parameters. Operative range is up to 3, or depending on the power, probably up to 7 kilometers, and frequency of antenna rotation is roughly 30 rotations per minute. Let's go further. Actually, how does it work? Because we have only one radar, we don't have another one to catch the signal. And from the school physics, we know that actually there is a specular reflection. Yeah, the incident angle equals to a reflected angle, and this is not the case. We need a backscatter mechanism, and actually there exists a backscatter mechanism. This is Bragg resonance, but not only that, because of the fact we have several scales, like actually a lot of scales of waves. The resonating waves, which are in a capillary area around 1.5 centimeters, they are modulated by the presence of bigger waves. Also, we could have this called tilt modulation. Also, we could have shadowing due to the partial occultation of wave troughs by a profile of bigger waves, and we have an effect of radar equation, which I will discuss a little bit later. So typically radar works in the pulse mode to save the energy and to make possible to operate in a resolution cells, in a range resolution cells. So the pulse duration is typically 50 nanoseconds, so it's pretty short pulse. Pulse repetition time is around 3 kilohertz. And so, for the range resolution, we have the following expression. C is the speed of light. This is a pulse length, and the theta is incident angle. So here is a schematic picture of the radar probing. with a side-looking radar, which can move on maybe airplane or just turn around its axis. The principle is the same. The azimuthal resolution is defined by the beam width in the azimuthal plane, and actually it's due to the diffraction limit. It's lambda electromagnetic divided by the size of antenna. Cannot be more. Sorry. So let's go further. The radar equation. Actually, we will see on the actual images that we have rather strong range dependence of the backscattered intensity, and it is due to the purely electromagnetic effect called radar equation, which connects the transmitted power and received power, the range, antenna gain, effective antenna area, and what is the most important, sigma is the radar cross section. It's actually what we are measuring with the radar. The most important thing is the trend R in power minus 4. The sigma, normalized radar cross section, is defined like this. Here we have also range. S actually is area of the target. This is the field in the far zone. This is the field near the radar. So this is an actual image collected in the FINA 3 research platform by X-band radar with VV polarization. You clearly see that strong range dependence of the signal, and you also distinguish some wave pattern, which actually is a wave pattern. But originally, these radars, as I already mentioned, were used for navigational needs, and this signal was considered to be a C clutter. But actually, it turned out that the signal contains a lot of useful information. So, a little bit of theory. We could consider the surface as a random function with defined statistical parameters. In particular, we assume that the mean value is equal to 0, and RMS deviation is constant, doesn't depend on the coordinates. Now we need to understand, because we want to use a perturbation theory, we need to understand what does it mean small roughnesses. Let's see. So if we have a steady function, not moving function, maybe still random, but due to the presence of roughnesses, the incident wave need to take a shorter distance. You see, this line is how it could be if we took specular reflection, and this is the track if we actually reflect from the wave itself. So this difference is psi of x cosine theta 0, and it goes to the reflected field. And if we make a simple manipulations, we will see that we have term like this in addition to the sign, and this term needs to be sufficiently small. And this condition is called the Rayleigh criterion for the smallness of roughnesses, because here we could put not the zeta but the sigma of zeta, naturally. So again, summarizing all the results, we have a reflected field as a sum of 0 order, which is basically specular reflection, and the first order, which is resonant mechanism. I don't have much time to go into details. I just point out that if we have the simplest case, the auxiliary problem with the one harmonic, in addition to the specular direction, we would have two symmetrically on the sides of the specular one, and fulfilling this condition. And to understand, is it possible to have a backscatter? It's actually pretty easy. I will skip this one. We'll show now. We just ask for this condition that for to make the projection of this additional reflection direction to be opposite to the projection of incident wave. And if it happens, it means that we have backscatter. And for grazing incidents, it becomes really simple expression. Lambda resonance of wave is approximately lambda electromagnetic divided by 2. So let's go further. Yeah, but as I already mentioned, we don't have only resonating ripples, we have other scales of waves, actually a spectrum, yeah? We have a spectrum, and it is reasonable to make the following decomposition. We use this random function. It's a resonant capillary waves with a narrow spectrum near the resonant wave number. And this is the slow variations due to the longer waves. And for this small scale part, we assume the conditions of disturbance theory. For large scale, we assume the geometric optics conditions. So let's go further. Now we discuss a bit the conventional methods of radar images processing. Here you see one example of actual radar image from a radar with HH polarization. You see also kind of wave patterns in the coastal zone. And this is the square actually we use to make a Fourier transform. This is only one image, but we use the time sequence. So the big advantage of the radar is that it gives both the spatial coverage and the temporal sequences of it. So it enables 3D analysis, which actually it's rather hard to do with other kind of tools.
How often does it read in time? Like what's the time you're getting a read in? What's the time is
like rotation period, it's 2.4 seconds. Yeah. It's like not, it's assumed to be quasi frozen, but actually it changes. Situation changes. Again, this is the zoomed picture of image, and this is already the Fourier spectrum. It's supposed to be three-dimensional, but we did the averaging of the angle in Fourier space, and we got k, modulus k, and omega in radian per meter and radian per second, respectively. What is what here? Firstly, there is a dispersion relation curve. This means that the signal from waves should lie here. We have signal from the beginning of coordinates, which is supposed to be, like theoretically, it's supposed to be a signal from groups of waves, or maybe non-linear waves. And the second harmonic, actually there can be second, third, fourth, and so on and so forth. It is due to the both nonlinearities of waves, like bound waves, and but mostly due to the fact of shadow presence here in the image. Further. So the conventional method is more or less, we use this dispersion relation shell filter, because we take a tiny neighborhood of this dispersion relation and fit it, because we don't know currents by default, and we might be that we don't know bathymetry. Yeah, so we need to fit this actually 3 parameters, and it's possible, people are doing this. Here we assume that current is uniform, that we have uniform current, that, which doesn't change with depth. Okay. So this is the definition of dispersion relation shell filter. We have here finite depth, we have current, And this is a kind of indicator we use to filter out the wave harmonic, high harmonics, and then we also have this. If we erase the effective signal, we have also kind of spectral noise pattern, which might be also interesting in some applications. Here are definitions of filtration for wave harmonic, for high harmonic, and here is background noise. Okay, here. What is really interesting, actually, it is a distribution of energy along this curve, which we can obtain easily. And you see here, this is results of simulation, because in simulation you could put a pretty nice and smooth spectrum, like a Jones swap or something else. Simulate the surface, simulate the radar images, and then see that actually the omnidirectional spectrum will look like this. So it deviates significantly. So that means that there exists some modulation transfer function between actual wave amplitudes and the amplitudes we get from radar. This mostly empirical modulation transfer function, because theoretically it's rather hard to investigate this problem. So what we could get? We could clearly get the peak of the spectrum, and it's already a lot. Even the peak wavelength, and also a peak direction if you look in another projection. Yeah, we could retrieve the significant wave height for this correlation. The problem is that these coefficients need to be fitted with use of in situ data, which is rather complicated, and the changes, if you change the radar location, the distance, and a lot of things, it will change. So it's not very nice method. Yeah. Let's go further. Yeah, this is a simulation, stochastic simulation of Raph's surface. I use in the simplest case, everything is homogeneous, nothing changes. Actually, what is random here? The phases are random, uniformly distributed. The amplitudes are defined in accordance with the spectrum, which consists of omnidirectional spectrum, let's say Jones swap part, and the directional spreading, let's say in accordance, I used the Mitsuyasu et al. 1975. This value is actually a Rayleigh distributed value. Actually, I don't like to use. I don't recommend you to use also. Actually, it's enough to save this random phase, and here to put only 2 multiplied by this thing. Here's the scheme of the radar probing, and you see here more or less how the shadowing occurs. The shadowing I calculated using the simple criterion based on the comparison of incident angle at each point. Don't want to go much for the details. And the tilt modulation is more or less proportional to the scalar product between the local normal, external normal vector, and the vector looking to the radar at each point. Which kind of makes sense, yeah? The maximum backscatter will be when they look at the same direction. Yeah. This is the formal definition. Probably don't need to stay a lot here. Yeah, actually what we get. We start from the simulation of Raph's surface. As in radar performance, we use polar coordinates to calculate the shadowing mask. Then we interpolate it to some Cartesian grid. You see here, this is shadowing mask, this is still modulation, together with shadowing mask, and this is with added speckle noise. It's a Gaussian noise, but not additive one, but multiplicative one. So let's go further. This is the conventional method of inversion of radar images. The idea is to filter everything except the first wave harmonic, which we fitted, and make them inverse Fourier transform. Yeah, and we get picture kind like this. you see the dotted line is the original. It's of course on the cross section. It's original, and the black line is reconstructed. So we see rather significant discrepancies here. Generally on the level of 15% of significant wave height. So could be better, yeah. So
What means original?
original, that one I simulated on the computer using that formula.
Oh, so and the other also was simulated.
Radar, yeah, everything was
Everything was
simulated.
simulated.
But believe me that if you compare with the papers, which are dealing with real images, it's more or less the same thing. At least in the sense of this modulation transfer function. So it's reasonable approximation. Okay, so now I will focus. How much time I have?
10 minutes.
10 minutes, not good. Okay. I need to run fast, but you know, if I don't make an introduction, probably people will be lost because it's something new to the society of pure pure mathematicians. Okay, so one of the problems of particular interest is the shear and current profile reconstruction. We have a vertical profile of horizontal velocity u of z. And without going into details, it is the governing equation is the Rayleigh equation. Together, this is the combined kinematic and dynamic free surface boundary condition and the condition on the bottom. So here the W is the vertical velocity profile. U, as I mentioned, is horizontal velocity profile. K is wave number. C is phase velocity, and C0 is phase velocity if you assume only finite water depth, no current. Let's go further. Here's a little bit of literature overview. Just you can read it. I don't read it again. And what is really interesting is Scope's solution. He derived in 1987 for finite water depth, which is really interesting for coastal zone. This is rather ugly expression, but it can be performed nicely with the hyperbolic trigonometric functions if you want. C0 you see here, only the finite water depth, nothing else. Yeah, and the idea was, okay, it's nice inverse problem how to try to reconstruct the profile while we are looking only on the surface. But the idea is that different scales of waves, different wavelengths are sensitive to the current on a different depth. But not like that. This dependence is not local, yeah, as you saw that in integrals. But we did a simple thing, just use a discretization of this expression with the trapezoidal method of integration. Then we go to the least square method, and which leads to a matrix formulation with the matrix elements like this. Here it's already with the hyperbolic trigonometric functions. This coefficient is pi n m pi n n. Actually, is a function like this, so it looks a little bit ugly with the heavy side theta function, but it's like this. It starts from 1, then 2, and then 4. Yeah. And what I did, actually, I tried to reconstruct different kind of profiles, let's say linear, trigonometric, parabolic, and exponential, with original data, no disturbance. Because it is inverse problem, probably the method is so bad that it will not treat even the clear data. And we see here it works. But as we could expect, we need to make a regularization to get a reasonable result for contaminated data, or what even worse, the data which jammed through the all these radar radar imaging mechanism. It's a little bit of reformulation. We just introduced a trial solution. We could say, okay, we know an a priori information that our profile, it looks like this, like 2 layers, maybe linear or something like that. And there will be a finite number of parameters which the system will adjust, in the end. And this is reformulated problem with the same matrix. I here is an identity matrix. Lambda is Lagrange multiplier, which means that if we take very small lambda, it means that our solution doesn't deviate a lot from the real solution. If we take a big value, it means that we trust to the trial solution and it will stick to the trial solution. Okay, here are results for the noise contaminated profile data. You see it's rather small standard deviation.
What is red line? What is black line?
Yeah, red line is original profile, and black line is reconstructed actually. And you see with non-regularized data it works pretty badly, and for regularized it's much better. So, and finally I tried to make an experiment to do all the procedure of radar imaging mechanism, to extract the dispersion relation data from the actual simulated radar spectrum. And I got pretty nice results. For here it is only for linear profile, but I got mostly the same nice for the exponential profile. Okay, maybe 5 more minutes. Yeah, and finally the last problem, it's pretty fresh results. There we wanted to try to see not the homogeneous signal, but the signal changing in space. Not on time, but just in space, due to the change of bathymetry. We used concept of linear shortening, could say like final slope equation, like linear version. And to treat this, the Fourier method doesn't work anymore, because Fourier method assumes spatial periodicity. So what is the alternative? Actually, there are 2 of them. It is windowed Fourier transform, or we tried the wavelet analysis. I put here the formal definition what is wavelet transform. F is a signal. It's assumed to be arbitrary integrable with square function. Psi called the mother wavelet. B is a coordinate shift, and A is a scaling factor. A is not equal to 0. The asterisk denotes the complex conjugate. So the mother wavelet should fulfill the admissibility condition. It's like formal definition, not that much interesting. For practical use, for mother wavelet, for wave application, people are using Morlet wavelet. In simple words, it's actually a harmonic function, like localized, with a Gaussian envelope. Yeah, and to do a very to make the procedure more computationally efficient, we do a small trick, just changing the scalar product to a convolution, and do a trick, just go into the Fourier images, which makes the convolution to be just a multiplication, and from that we do inverse one, which is identically equal to the desired wavelet's transform. Just a small mathematical trick, but it's very efficient. Yeah, here are the results. Maybe you're more interested to see on this. This is a time range diagram of one harmonic Scholling, and here is the spectrum Scholling. You see here is the bathymetry, here, and here is the cross section. You see what's going on actually. In the linear Scholling, we have a shortening of waves and the growth of amplitude. The spectrum behaves a little bit differently. Okay, if I don't have much time to go that much in the details, But you see the KH, the dimensionless depth, say that we are already in the shallow water, or here we start from intermediate water. These are the nice pictures of wavelet spectrum. Picture depends on the coordinate, on the range, and the pseudo wave number, because as you remember, we had only a scaling factor, which is something inversely proportional to the pseudo wave number. Yeah? This is for one harmonic, and this is for spectral case. Here is the procedure. How did we want to adopt the conventional method to work with the wavelet analysis? We do more or less the same procedure as for Fourier, but in a wavelet space, applying combined high pass and low pass filter with a modulation transfer function with power which a little bit differs from that for Fourier analysis. Phase shift correction here it's simple, but actually it is a problem for Fourier analysis because this is quarter of period of local wave, and the period changing gradually while it's showing. So the wavelet is ideal for this case. And again, the inverse transform and the calibration. So here's the difference map. You see the T averaged error and the probability of shadowing. You see as probability of shadowing grows, the error grows, which is kind of logical in this case. This comparison on the section. Here you see the original relative elevation, the radar image on the section, and here the comparison of original and reconstructed. Pretty not that bad, yeah? Is it clear? What's written? You see here you have a quarter period shift of the local wave, and also its noise, which we need to filter out. Here the same for the spectrum. Again, the correlation coefficient is perfect at around 1. And here is a summary of error analysis. Actually, the only problem is here that we can't do the filtration in a 3D space. Like in a Fourier space, we could do this in a way that it's not completely clear how to do. And that's why the high harmonic survives. And they are the reason, they are the sources of these sharp shortcuts in the shadowed errors. Probably in the real data, this will not be such a big problem because nature is more smooth than our simulation. So, but here, just to compare, for rather high radar, you have error on percentage of significant wave height on the level of 4 or 5%. So it's much better. So thank you for your attention. Any questions?
Thank you. Any questions? Time. Enrica, please.
So actually I arrived late, I'm sorry, but I just have a question about the shoaling that you said. So was that I mean, like, there were two pictures, I didn't quite understand. Did you, I mean, what did you do there? I mean, so, harmonic shoaling. So the left, I mean, so how did you construct the two pictures? That's what I mean.
No, actually, everything here, it's first of all, it's linear shoaling. We don't take into account the interharmonic interactions.
Right.
Here, everything is in accordance with the waves conservation law.
So basically, it's
So
a
the
formula,
energy flux
the left.
conservates.
You just use the shoaling formula.
Yeah.
Yeah. Right. Okay.
But here, for one harmonic, and it's clear how it behaves.
Yeah. Sure.
For the spectrum, it's a little bit more complicated.
Oh, I see.
But the nice idea here also, I need to mention this. If you look at this wavelet spectrum, and if you can trace the peak K, or in this case, this is the only one K, you can reconstruct the bathymetry. Because you do know the dispersion relation omega doesn't change, and you can solve for H.
Yeah. Yeah.
This is maybe a topic for the next paper. Okay, thank you for attention.
Well, can you recognize floating bodies by radar? So your analysis.
Like
floating bodies
on the
like
surface?
ice. Yeah.
Like ice.
Ice pieces, for example.
Yeah, I
To
guess.
relate your presentation to.
Yeah, I guess yes, especially with the pieces of ice.
Yeah.
With the cracked ice, it should be possible.
Yeah, but the pieces, broken. And also kind of ships, small boats,
Yeah, ships, for sure.
they're visible.
They're very clearly visible.
Very clear visible.
Those radars that they use,
Yeah,
they're
it's
not-
originally
they're
designed
navigational,
for
they're designed
Yeah, to
seeing
see
ships,
them.
yeah, and big bodies in the
Could
water.
be in bad weather or at night, right?
Yeah, yeah, that's an advantage.
Uh-huh.
clearly.
And as I understand, by the radar, it's much simpler to measure directional spectrum
Yeah,
than
it's possible.
by buoys, right?
So direction spectrum, you
Did you try? Because there is many problems with measuring the directional spectrum by buoys. By radar, it's can be better. Can you? But on the other hand, there are several techniques how to by using that buoy measurements to reconstruct the directional spectrum. But if you can simulate the directional waves, find them by your simulations, you are simulating radar as well, and then to compare it with the techniques like by Lighthill and not Lighthill, Longy Higgins. Longy Higgins in 60s first derived that directional spectrum from one buoy measurements. Then it would be interesting to know how to behave, because buoy is a quite usual device for measuring, but it's a scattering is, I mean, not scattering, scattering or accuracy is very bad. I mean, we do not know actually what's happening, because just 2 degrees of freedom, and we are talking about directional spectrum, so it's something strange. But
Yeah, actually, it's an interesting question, and I don't think that someone looked at this up until this point, but it's really nice.
So can you get a directional spectrum from it, or is it just a dominant direction?
kind of. Definitely, it's not exact directional spectrum. It's something. It's like by cosine, you know, that in the cosine theta angle in the power 2s, and it could be also some shift or something. So it's more than
Parameterized.
yeah, parameterized with, because there are not enough degrees of freedom. We just 3 degrees of freedom we measure. I mean, vertical.
But here.
No. Here we measure
surely,
everything.
Yeah.
Here we measure everything. Yeah. This is
So in
why
the buoy, there are only 2 degrees of freedom?
not 3 degrees of
3,
freedom.
yeah.
3 degrees of freedom.
Yeah.
There are also some of them.
Yeah.
They measure angles.
Yeah,
Yeah, but all together it could be okay 6.
yeah.
6. But still it's not enough. But actually 3.
Right.
Actually 3. The standards they are 3. So yeah, this big problem to to do something. On the other hand, the buoys are everywhere. So they used to measure something, but not clear what.
Now the radars are also everywhere, so
Oh yeah.
especially the HF radars, which are
And potentially, I understand this can be installed, say, on the Spitzbergen or somewhere to measure that broken field, and to measure that distribution of sizes in size of the floors, right? Or it could be motion even, but distribution at least, yeah. So that is the. And I believe it's very possible.
They have a lot
because
of data actually.
Yeah, because with the floating pieces, they are not necessary, but they are solid, right? So less degrees of freedom.
Yeah.
Okay, 6 degrees, so 6 degrees of freedom, but it's not like for water where it's for free surface where it's infinite degrees of freedom, even for finite piece of free surface.
What information do you want to get about the ice bodies?
I believe it's like distribution in size.
Yeah.
And Dave, and could be even that waves propagating in ice.
Yeah, waves.
I think so. I think
Most
so.
probable it's waves.
Yeah, I think even it's possible. Could be possible to concentrate rather straight or focus it straight on the pieces, not on the free surface, but pieces. I don't know is it possible or not. Saying, yeah, there are many of them. So I take from the from that data only point on the floating piece. That one, and then 6 degrees of freedom, but without doing anything from the free surface. I believe it's possible. Could be.
Yeah, I think
possible.
so. I never saw the data. And, the only question for me is the backscatter mechanism.
Yeah, the Spitsbergen, Henry can confirm it is the best place because it's open water now, right?
Actually, I'm not sure, I'm sorry.
I think.
Actually, to be honest, I actually do have a data with ice.
Okay.
I just didn't check this because, you know, it's a lot of other things to do. But I do have it, and it would be maybe nice to see.
From Germany. Not from
Germany,
Israel.
yeah, Germany, exactly,
yeah,
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 yeah.
German,
Exactly
everywhere,
that.
doing everything. Sure, they are very good. Yeah, and final, could be final question for me. Did you show any comparison of, say, your theory, actually it's theoretical, right, with measurements? I mean, with actual measurements.
Not yet.
Not
yet, because
Are you-
unfortunately we just installed the
Do you
radar.
plan that
yeah.
to finalize your
this
PhD?
year.
To
This
finalize
year.
your PhD.
Because we just have a radar, we need to install it, and, you know,
But
start
also,
checking on it.
who is not clear, I try to imagine what you can compare. Because to compare, you need to know actually what's
Yeah, the
happening,
individual
then
things
what the
are
radar
the
give you,
problematic.
and so there are several pieces of this puzzle.
But let's say for individual waves, there are approaches, at least to give you an idea what's going on. You can install the chain of pressure cells. Partially.
Yeah, oh yeah. Okay, thank you very much. Then we go to the presentation.